So yes, welcome back to the class. And we were discussing about thermodynamics.
Mhm.
So in thermodynamics, we studied various laws and how heat actually moves. What about work done? How can we calculate it? What
Mhm.
is internal energy? What are state functions, state variables? We discussed a few technical terms related to it. Now, in today's class, we are going to look about what are the types of heat exactly we can differentiate depending upon various conditions. So
Mhm.
that thing is basically referred as heat capacity, or specifically specific heat capacity
Mhm.
for an individual type of element. Like for example, suppose I have some ice and its initial temperature was about 15 degrees Celsius. I just put it on a stove and started heating it.
Mhm.
So you tell me what would happen.
It would melt.
Like what happen if I put it on a stove, increasing the temperature, basically heating it? What happens to the ice?
Yeah, then the ice will melt.
It will melt. Melt to become what?
Water.
Water. Suppose I didn't switch off that stove and still heating it. So what would happen?
What do you mean?
Like I'm still heating it. So what
Yeah,
would happen to the water?
but you're saying you switch off the stove.
No, no, no. I'm saying that I'm still heating it. So initially it was ice, now it becomes water. I'm still heating it. What would happen to it?
Oh, then the water will start boiling.
Water would start boiling, it will start evaporating,
Mhm.
and later on it will convert into steam.
Mhm.
So basically here we have seen that heat is something which can cause state change,
Mhm.
or you can say if we are able to vary temperature, that can be seen as that the whatever element we have, it might change its state depending upon how much heat we are giving it. So here let us look more technically now, that what would exactly used to happen. First, initially ice was 15 degrees Celsius. The temperature increases, ice will come to 0 degrees Celsius, because we know that 0 degrees Celsius there exists ice.
Mhm.
Now this ice at 0 degrees Celsius will convert into water at same temperature, right?
Mhm.
Then if we continue heating it, then that water will convert into water at 100 degrees Celsius, because this is the range where the state change takes place, and in between there is no state change.
Mhm.
Now, at 100 degrees Celsius, water is again going to change and change its state and becomes steam. So now we'll have steam at 100 degrees Celsius. Now, if we further heating it, in case of boilers, this happen that we heat the steam, for your knowledge. So that steam will reach to whatever temperature we want. But again, we can raise the temperature of steam also.
Mhm.
So basically, I want to explain this particular thing is that in every change of either state or temperature, there involves a specific heat. Like we are talking about ice, so there must be some sort of specific heat of ice. So to be precise, here involves specific heat of whatever matter we have within temperature change. When there is a state change of that element, there involves latent heat. Then again, we can see there is a temperature change only. So there involves specific heat. Basically, we are going to calculate each of these things. So let us understand that where they do actually exist.
Mm-hmm.
Again, when there is a state change, there exists a latent heat. And then where is a temperature change involves, there exists a specific heat. So when we are melting or we can say converting some sort of element into its state change, then there involves several heats. So in order to calculate that how much energy we have actually supplied to this 15 degree of ice in order to convert it into steam at some T degree Celsius temperature, we can calculate that total heat given to the ice. So we will be calculating that here.
Mm-hmm.
So specific heat, if I define it, it is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. So whatever amount of change involves, like temperature wise, that here it involves 15 degree of Celsius. That is a change. So whatever value of 1 degree Celsius that substance has, we'll multiply it with 15 degree Celsius of change,
Mm-hmm.
and we'll get that heat which is required for this specific conversion. It's called specific heat. Whereas when we're talking about the state change, so it is simply defined as amount of heat required to convert 1 gram of ice into water. That is latent heat. So in order to calculate this latent heat, we'll multiply total mass of whatever substance we have into that latent heat value of that particular substance. Like in this case, its size. So this is how we are going to calculate specific and latent heat. We'll do some problem and I'll get to know about it more clearly. So the question is, I guess you should try it out.
Mm-hmm. A.
The thermal capacity of any body is measure of its capacity to absorb heat. Let's see the other options as well. B says a measure of its capacity to provide heat, quantity of heat required to raise its temperature by unit degree Celsius. So that thing is basically specific heat. C cannot be the option, that for sure. The
Mm-hmm.
quantity of heat required to raise the temperature of unit mass by body by a unit degree. That is also something related to specific heat only. So yes, your observation is correct. It is a measure of its capacity to absorb heat. Again, I guess you can also try this question. Try it out.
Mm-hmm.
Okay. Remember the question and look at it once again, like this whole thing. What is exactly happening? Now, after this, look at the question again. Maybe you can answer.
Mm-hmm.
Done?
Yeah.
Now read the question again.
Oh, the latent heat of liquid.
Latent heat of liquid. It's asking about dE. So from here to here, it should be liquid. It should be ice. Here to here, it should be liquid. And here to here, it should be
Oh,
steam.
wait, I don't understand why actually.
See, what happens first? It was ice
Yeah.
at certain degree Celsius converted into ice at 0
Mhm.
degree Celsius.
Yeah.
So here it will represent this part of graph. See how temperature and heat input changes. So at 0 degree Celsius, it was ice and its temperature will be more negative and it will stay as ice. But here from O to A, temperature is increasing, heat input is increasing. This means it must be converting or increasing its temperature. Now this must represent state change because state change happens at single temperature. So for uh, ice, it would be 0 degree Celsius.
Mm-hmm.
Maybe it should be 100 degrees Celsius. Or to be precise, it should be like that. So this should represent ice. This should represent water. That's why EDE part will act as steam, increase of temperature of steam.
Mm-hmm.
That is vapors. So it should be latent heat of vapors.
Mm.
Understood?
Yeah.
Okay, try this one out then.
Mm.
So basically, here this C is specific heat.
Mm-hmm.
So I won't talk about that how this relation came, but this relation is required to solve this problem.
Um, it would be C.
Okay, let's see. Q by M delta T, that would be specific heat capacity. So Q will be base and it will be perpendicular. So slope, if you talk about slope, so who has more slope according
Um,
to this relation?
A. Like, are you
Hmm.
asking like out of A, B, and C, which one has or
C. C is directly proportional to Q according to this relation,
yeah.
and it is inversely proportional to temperature
Mm-hmm.
change. So if there will be less temperature change, if it is less, heat capacity will be more. And
Mm-hmm.
if Q is more, heat capacity will again be more. And this thing happens for C, which you said earlier. So it was correct. But you should know the logic. I don't know what logic you applied, but this is the correct logic to look at this problem.
Mm-hmm.
Remember the relation. This is again that specific heat I talked about. So whatever heat it is required to do that change, temperature change, we should multiply the mass first with specific heat of that element, whether it is liquid, like water or ice or something, multiplied by whatever type, whatever temperature we are changing for it. That
Mm-hmm.
change in temperature, we should multiply this. We get that heat required to do the change.
Mm-hmm.
So here, that heat involves specific heat. So if we rewrite this equation, we'll get Q by M delta T. So Q is represented by x-axis.
Mm-hmm.
So if C needs to be more, this needs to be more. And this is temperature. So if C needs to be more, temperature should be less according to this relation. I
Mm-hmm.
simply applied it and found C is the correct answer. All right, let's move ahead. Let me do it for you. Just look at the question. So basically, I'm letting you know the how to calculate that energy. So the how much heat is gained by 5 kg of water at 20 degrees Celsius. Like there was initially we have water
Mm-hmm.
at 20 degrees Celsius to brought it to its boiling point. So now what we did is we brought this water at 100 degrees Celsius. So what type of heat is involved in this process? There is no state change, only temperature change. So it must involve specific heat. So we have to calculate that specific heat. So that delta, that Q we found in the last equation, that Q is this specific heat. So it is mc delta T. Now what is C? C is the specific heat of water here.
Mm-hmm.
So that C is something which is constant. Like it is specific. This number is specific for certain compound, element, matter, whatever it is there in the question.
Mm-hmm.
It is constant for that material, 100%. And most of the time that question and that constant's value is given in the question to put it and solve the value of Q, like what is specific heat involved in this relation. So that is a constant, it must be given in the question
Mm-hmm.
itself. Temperature change, it is temperature change, and we can easily see that there is 80 degrees Celsius of temperature change. Mass is given as 5 kg.
Mm-hmm.
C is something specific heat of water. It's not given in the question, but wait, let me check its exact value. We can directly put its exact value in the question. Again, it's constant, so its value must be given. You should not require to learn it.
Mm-hmm.
It's 4.184 joule.
Mm-hmm.
That C for water is 4.184 joule per gram. So it is for per gram. We have 5 kg. Now let us calculate that heat. So that Q is nothing but M. That should be in kg. But according to this relation, it should be in grams. So 5,000 grams times C. This is this value of C,
Where did
4.184.
you get 4.1, like how did you calculate 4.184?
I didn't calculate it. This is the data.
So are you already given this or like
Yeah,
cuz
it should be given in the question. That's what I said. If this kind of question is there, this value of C is must be given in the question.
oh
Somehow it is not there in this PPT, but it should be given. That's what I'm saying.
mm-hmm.
So 5,000 times 4.1822 delta T, that is temperature change, and that is of 80 degrees Celsius. So just calculate its value and tell me it matches with which option.
Mm-hmm.
Again, its unit is kilojoules. So answer must be 10,000 times to this
Mm-hmm.
in joules. And from here you'll be getting value in joules.
Um
So that conversion is also involved here. Calculate it and
I
tell me.
got A. Like I got yeah, like
1680. Yeah. So A is the correct answer. All right.
and where
Let's
did
move
and
ahead.
one more question, where did you get 80 from?
Where would I get what?
Where did you get 80 from?
Okay. That 80 is temperature change, delta T.
Oh, okay. Got it.
There is a 80 degrees Celsius of temperature change, so that's why we got 80. All right. Let me do it. This is how we calculated it. We
Mhm.
substituted the values. All right, let's move ahead. So one more question is there. If you want to try, you can, or you should move ahead. Like if you actually want to try it, just try it out.
Okay.
You can't calculate it orally. You have to use notebook and pen.
Okay. Is it using the same equation that we used?
Yeah, but it's little different. Oh, I got it. We should do it. It involves something else, like another case, you can say. So I think I should discuss it. So the question says there was 10 kgs of ice at minus 10 degrees Celsius. So you can assume that here I had ice at minus 10 degrees Celsius and it is mixed with 40 kgs of water at 45 degrees Celsius. This is some other case. Let us see. So it is mixed with 40 kgs of water at 45 degrees Celsius. So questions nature of the mixture, final temperature of the mixture. So it's let us take it in comparison with some real life example. Suppose you had ice and you just put it in a boiling water. So what would happen with the water? Like what about its temperature?
It
In
would
water you just put ice.
it would decrease a bit.
Yeah, the temperature is lowered by some degrees, you can say.
Yeah.
So here also, I guess the same thing would happen, but the temperature change, but you can say the water temperature change would not felt much, although it would be decreased for sure because you're mixing 10 minus 10 degrees of ice with water, which was at 45 degrees Celsius. So
So 35?
yeah, we can say not exact value. 35 is not the exact answer, but yes, because you can see that there is not even a single option there, so that cannot be the answer. So how should we calculate it? So it basically involves some other heat related principle, and that principle is something which can only be explained through problem. So that principle is principle of calorimeter. Principle of calorimeter, we can say. The principle says whatever heat is lost by some type of matter during mixing, that heat must be gained by other element
Mm.
present in the mix. Very simple principle it says. So just tell me one thing. What do you think out of these two, which element has gained that energy and which element has lost that energy according to your observation? That change. I'm talking about the change.
Out of which two elements? The ice and
There is ice and there is water. You mix them both. So I'm
uh,
asking which element gain energy and which element loses it.
oh, the water gained energy and the ice lost energy.
No, it's not like that. Basically, ice was at negative temperature. So if
Mm.
something is at negative temperature, it simply means that there is no energy left in it. Like let me relate it with you. When a human dies, his whole body become a little bit cold, if you
Yeah.
know this. Why? Because the particle has lost all of its energy, the
Mm-hmm.
temperature down. Similarly, ice was at negative 10 degrees Celsius, so there was no energy in it. So
Oh.
it was the one who actually gains energy and who loses it? water, what was that, which was at 45 degrees Celsius.
Oh, yeah.
So, so here we can say that ice gain heat, which is equals to what amount of energy this water has lost. So how can we calculate this? That what amount of this ice has gained and what amount of heat that water has lost using the same relations which we used earlier. So ice must have gained some heat. So how would ice use that heat? That is what we should think. So ice is something which was at minus 10 degrees Celsius. So if we get enough, like think of it this way, first it will try to get energy to convert itself at 0 degrees Celsius. Like this is how energy flows, right? This is what we have seen.
Mm-hmm.
And then whatever extra energy it gain, that ice would convert into water at 0 degrees Celsius change. Then this water would try to gain some energy at that delta T degree Celsius. So whatever amount of extra energy it will get, it will then convert into water at some degree temperature. Whereas if you look at the energy change for this water, how would it goes? Let's see. So there was 40 kg of water at 45 degrees Celsius. Now it is losing heat now. So now how that lost actually seen. So 40 kg of water के साथ with 40 kg of water, what happens is it will comes to some T degree Celsius temperature.
I
It
understand
is
it, by the way, if you speak in between, so don't worry about it.
uh, like Henry. Yeah, obviously.
Yeah.
Yeah.
Mm-hmm.
Generally I don't use, so don't know how.
Yeah.
So 40 kg water was at T degree Celsius.
Mm-hmm.
So this T degree Celsius and this T degree Celsius for both would be same. This is something we call equilibrium,
Mm-hmm.
like where both becomes some in some conditions equal. So here it's temperature. That is called thermal equilibrium. So let us write it in the form of equation now. What is the change? Specific heat. What is this change? Latent heat. Matlab this involves this kind of heat exchange. Again, specific heat. In this case, only specific heat. So how we would write it? Specific heat of water. Specific heat of ice first, plus latent heat of ice and water, plus specific heat of water.
Mm-hmm.
This must be equals to specific heat of this water at 45 degrees Celsius. So if we write it in the form of equation to calculate the result, this Q must be mc ice delta T. This latent heat must be mass of whatever it is converting into, sorry, is changing its state from this into latent heat, that is L.
Mm-hmm.
And again, this delta Q water is going to be mcw, that is a water delta T. Whereas here it will be mcw delta T only, where this mass is mass of water, whereas these masses are masses of mass of ice.
Mm-hmm.
Because ice is something which is gaining heat, and here water is something which is losing it. So if we
Not the last
solve this,
one, right?
what?
The in the first part before the equal sign, the MCW, that one's not ice. That one's water, right?
No, no, no. But that water is something which comes from ice, na? Which was
Oh, okay.
initially ice.
Converted it. Okay, yeah.
So I'm
Yeah.
talking about mass.
Okay.
So that mass is the mass of ice.
Mm-hmm.
It is water now, but the mass belongs to the mass of ice. So if we solve this equation, we can get that delta T. And this is what it is asked in the question. So not an easy problem if you look at the
Mm-hmm.
way it was calculated, need to be calculated. But if you understand it logically, like if you feel that heat exchange, that how heat is required to change the state or heat is required to raise or decrease the temperature.
Mm-hmm.
If you can feel this, like actually by looking at something, then this will become very easy
Mm-hmm.
because there is rarely two formulas, mc delta T and ml. This
Mm-hmm.
is mass of the element or L is the latent heat of whatever it is. So it would be ice here. So latent heat of ice is given 2100
Mm-hmm.
or specific heat of water we simply saw earlier. It was 4.18 joule per gram.
Mm-hmm.
So you can compare it. Like for water is 4.184, whereas for ice it is 2100. Like it's much. Although no. It is kilojoules. I made it wrong.
Mm-hmm.
It converted to joules per gram, it would be 2.1 gram per joule per gram. So water specific it is more, not the ice.
Mm-hmm.
So if you solve it, we'll get the answer. So what you can do is whenever you are revising, just try to solve the value. Find delta T here. So when you came back to this page, read this note and try to get the value. Okay.
Mm-hmm.
Now what are the relations between specific heat? They are nothing. MC delta T is delta Q, and that Q is specific heat. Then there is ML, which is again delta Q, which is latent heat. So these two were the relations which we used.
Mm-hmm.
Now it is the last part of the chapter, last part of thermodynamics. Ideally, we should have ended this yesterday, but I thought I should complete it completely. It should not be like that I missed something or
Mm-hmm.
it's not supposed to be done. All right, we'll try to start the new chapter today only. That's also I have. So, how many methods of heat transfers are there? This is our concern. Let us try to feel it. That how many types of heat transfer are there. Let me start it with sunlight, very basic form of heat transfer. If you know it somehow, then this is the case. This case is there for electromagnetic waves. Like again, it's a topic completely. So let me just explain it to you in short. Whatever sunlight comes from sun to earth, this is electromagnetic wave. It is not sunlight or something. So it is not light basically. It is electromagnetic wave. Or you can say light is an electromagnetic wave. So however you should take it, it is an
Mm-hmm.
electromagnetic wave, and it can carry energy from way long from sun to the earth.
Mm-hmm.
And the most amazing part is in between earth and sun, the these waves will actually act as waves, and whatever amount of heat they are carrying, they don't lose it. And
Mm-hmm.
the moment these waves enter into the earth's atmosphere, they started releasing heat. So these are like messengers from sun to earth which which sends us energy.
Mhm.
because ultimate source of energy is sun only.
Mhm.
So that type of heat transfer is something we called radiation.
Mhm.
This is one such type of heat transfer in which electromagnetic waves carries heat, where there is no actual transfer of matter. This is the main thing. Because uh, still now we don't know what is the mass of photon. Mass of photon, or you can say photons are the particles which are supposed to carry that energy from sun to earth.
Mhm.
These are those particles. So we are not able to find its mass, although we cannot even see it. We can feel it, by the way. We can feel that heat from sun.
Mhm.
Next type of heat transfer is that the very simple one which we discussed in the first class, conduction.
Mhm.
So that utensil experiment or utensil example. So that is conduction, which is again very similar. The last is convection.
Mhm.
Now the convection way of heat transfer is very unique. Again, everything is created by nature, but this is nature, or you can say this is that season change which occurs on Earth. So science has also keep this as another way of heat transfer because we see that heat transfer in summers there's hot, in winters it's cold. How it is happening, how that whole temperature of a region got changed suddenly within a span of 15 days. So
Mhm.
that is another way of heat transfer which we call convection. So these are three modes of heat transfer, and that is something only the name is something you should need to know.
Mhm.
All the rest is okay. So, any question on this? This three type of, are you able to feel it that how these are mode of heat transfers?
Yeah.
All right, let's move on. This is the, you can say almost conclusion of thermodynamics. Whatever we talked till now is related to law one,
Mhm.
like whatever we talked till now. So that application part was based upon law one. We have
Mhm.
another law of thermodynamics. We'll be talking about that law. And but this law doesn't have much explications. That's why we don't study it more.
Mhm.
So in order to understand this law, we need to understand a little bit of working of heat engine. Like this heat engine is something which you know.
Mhm.
We are talking about that engine only. So generally with that engine, what happens is that how it is able to do work. Let me talk about do you drive something?
Do I drive
Drive like
like a car,
scoot, not a car exactly, like two-wheeler or something.
a bicycle,
Mm,
motorcycle?
no, that's not a case. Yeah, motorcycle or something. Is there something like scooty trend in California?
Not really, not as much.
Okay, because here in India, like
Yeah, I
the
know.
first choice of
My
girls is
cousin
scooty.
has a motorcycle, so like he would take me every time we go there.
Okay, all right. So just consider that motorcycle only. What is the basic process of driving a motorcycle? First of all, you need to have oil, and that engine of your vehicle should be perfect,
Mhm.
and that oil gives us energy. That energy can be in any form. That engine takes that energy and does some work.
Mhm.
And what is that work? It moves us. And in physics, whenever there is movement, whenever there is displacement, we say there is work.
Mhm.
So, so that engine has done some work. How he's capable
Mhm.
of doing that work? By taking energy from the oil.
Mhm.
So the second law of thermodynamics says basically it has two statements. So second law of thermodynamics is based upon this part only.
Mhm.
Like This part of thermodynamics is commercial, to be precise. So almost there are so many companies working on it. They develop a different type of engines and they patent them. And later on, if it works, like in terms of efficiency, it was accepted by world. So this part is commercial. So only for this part, there are two statements, which is termed as second law of thermodynamics. The first statement was given by Kelvin and Planck.
Mm-hmm.
Again, they were the scientists, and they said that it is impossible for any heat engine to convert all heat absorbed from this. Like to this law says that it is impossible for any this type of engine to convert all the energy it gained from that oil
Mm-hmm.
into work. So and no engine can have 100% efficiency. This is what he was trying to say.
Okay.
Because what is 100% efficiency? 100% efficiency is something like whatever you take, like as an input,
Like it uses
you
everything.
can, yeah, it uses everything and it got converted into some output.
Mm-hmm.
It can be anything. So in this case, it's energy is input that is coming out from oil and it is being converted into work that is work
Mm-hmm.
output. So this is what the two people says. So in the commercial world, this is what the race is.
Mm-hmm.
Like I'll develop in such an efficient engine which will consume almost all of its energy and convert it into work.
Mm-hmm.
So this thing can easily be noticed in terms of actual examples around us. Like if you look at the size of the vehicle, it will consume more energy to
Yeah.
produce more work. Like if you look at the size of a very small engine like that of motorcycle, it is the smallest engine that exists. So that engine would require lesser oil to do the same displacement
Mm-hmm.
because the mass is different.
Mm-hmm.
So this was the first statement. Next statement was given by Clausius. He said it is impossible for a self-acting machine unaided by any external agency to transfer heat from cold reservoir to hot reservoir. In other words, heat cannot flow by itself from a colder to a hotter body.
Oh. Mm-hmm.
So this statement is also almost there for commercial purpose only. Like, see, let's look at this sector of something which some people somehow manage to get that it would become a that much great or bigger sector that we need to set it free for everyone. Like
Mm-hmm.
nobody is ever at this stage is able to create it such an engine which has 100% efficiency.
Mm-hmm.
So another statement is also something for like something for that only that nobody can ever create something. Matlab it can never happen on its own that temperature travels from cold to hot region.
Mm-hmm.
Like temperature is transferring from cold to hot region. It can never happen.
Mm-hmm.
This is what he said in his statement and said without any external agency.
Mm-hmm.
Matlab means he needs something every time to transfer heat from cold to hot region.
Mm-hmm.
So can you see any place where we are doing this? We are transferring heat from colder region to hotter region with using some external agency. Have you seen it somewhere?
Mm,
What is the average temperature of California throughout the year?
probably like
Is it on a hotter side or is it on a colder side?
probably warmer, like maybe like 60 degrees Fahrenheit. or
60 degrees Fahrenheit.
yeah,
Okay.
60, 65. Yeah. But it really depends. But yeah.
So you might not have felt that. Okay, try it out. Have you ever seen a region where you have seen that heat is being transferred from cold region to hotter region by using some external agency?
Mm, I haven't seen like mm,
It's not like that you haven't seen. Uh, might be the reason. Temperature. In ACs, it works like that only, or in refrigerators. So if you talk about refrigerator, this is what happens there only. What is refrigerator doing? Whatever heat is there in the food item we kept in the refrigerator, it
mhm,
extracts heat from it
mhm,
and make it colder, become colder. So
mhm.
that extra heat through outside in the surroundings. That is why we observe that the nearby place of refrigerator is somewhat a little hot in comparison to the rest part.
But that's hot to cold. What about cold to hot?
No, no, no. That is what I'm talking about now. It is taking heat from some body, like it is taking out heat.
Yeah,
This body is losing heat. How? How it is becoming colder? With the help of refrigerator.
yeah.
So I'm talking about this body which is kept in the refrigerator, which
Mhm.
say this that in that thing you are using an external agency refrigerator
Oh, okay.
and that food is getting more colder and colder.
Okay.
So this is what his statement is that heat cannot transfer from colder region to hot region
Okay.
without using external agents. Because the natural way of heat flow is that it flows from hotter region to colder region.
Yeah.
So external, if there is an external agency, we can do the reverse. This is what Clausius says.
Oh, okay. So you can only do the reverse with an external agency.
Yes. Otherwise, it would flow from hotter part to colder part.
Got it.
Again, that is the statement. No process is possible whose sole result is the transfer of heat from colder region to a hotter object,
Mm-hmm.
colder object to a hotter object. So we cannot process that change without using any other external agency.
Mm-hmm.
This is something which is more belongs to chemistry, although it's there in physics also. And also as well, it is the last thing that I was supposed to tell you. Entropy is something we call randomness. In motion, you can say. So it is specifically being taught for gases, that
Mm-hmm.
how random they are. They just move. So this is something which defines that degree of randomness, which is explained here in this entropy thing. That is called basically entropy, degree of randomness.
Mm-hmm.
So every gas has different value of it, and it defines that how energetic, or you can say that how much energy a gas carries. So if it is moving very fast, degree of randomness is high, so it would carry more energy, you can say, because it would have greater velocity, the particle has greater velocity. But if some gas is moving little slow in terms of its speed of the molecules, then we can say there is a little less randomness in comparison to the first gas. So its entropy would be lesser.
Mm-hmm.
So it is again represented by delta S. It is equals to ml by T, where L is again latent heat and T is the temperature. That what is the temperature at which that gas molecules is moving so faster. So that would give us entropy. Like if I give you an example, if you have seen a pest control and whatever type of gas this sprays in the house to remove mosquitoes or something,
Mhm.
or if there is some sort of pest control, I guess, then in that pest control, that gas suddenly moves so fast, if you have seen, like that the degree of randomness is so much, the entropy is so high. How is that possible? How we have done it? So by changing the temperature of it and how minimum we can do. So whenever they feel a maximum temperature change, the entropy increases.
Mhm.
So that's all about thermodynamics, and that's all about